Here we have the solution for test number 2. First of all, we go ahead and we put our name in and we get going. If there is only one force acting on an object, can the object's acceleration be 0? So the acceleration equals 0. This means, right, when we sum the forces, that's equal to 0. So the sum of the forces is equal to 0 means acceleration equals 0, because the first law gives us that. No change in the object's motion. If we have the sum of the forces equals ma, which is not 0, that's Newton's second law. Okay, so the problem says there is only one force acting. Let's take a look at that. There's the object. There's the one force. Is the sum of the force equal 0, like we see in the picture over there? Or is the sum of the forces equal to ma? Well, the problem says that the sum of the forces is equal to F. F is not 0. If F is not 0, then of course F equals ma, which is the sum of the forces, is not 0. And that of course implies the acceleration is not 0. If there is only one force acting on the object, can the object's acceleration be 0? No. No, the object's acceleration cannot be 0 for the reasons given over here. Second question. A 20 kilogram block is pushed across a horizontal surface with a force of 100 newtons. In the absence of friction, draw a free body diagram for the system above, identifying all the forces. We'll go and make the block to be a point. There is the force due to gravity down, which is mg. There is the normal force pushing up. And let's see, there is a horizontal pushing force of 100 newtons. I don't know which direction it is. It's either left or right, but there's the picture. And we're also given that Fp is 100 newtons. So I have a free body diagram. I have this force, its value, the direction of the normal force, direction of the gravitational force, and mg, that's going to give you 10 out of 10. You could also go ahead and actually write this in: normal force, gravitational, and push force. And then we're good to go. Next question. What is the acceleration of the block? Well, if we've got our free body diagram, in order to solve these problems, I've said, well, one of the first things you're supposed to do is write down what you have. So I'll do that. Mass is 20 kilograms. The push force is 100 newtons. In the absence of friction, draw a free body diagram for the system above, identifying all forces acting on the block. We have to choose a coordinate system. I'll choose up and to the right as positive. That means the way I've drawn it in the picture, this is plus 100 newtons because the force is to the right, which I've said is positive x. Let's see. The normal force is up, etc. What is the acceleration of the block? So to solve the problem, we choose x and y coordinates, and we're going to go ahead and first of all sum all the forces in x, and we're told that the block is moving. So the sum of all the forces in x is Fp, which is 100 newtons, and that's going to equal max, or we can say 20 ax. Therefore, the acceleration of the block is 100 newtons divided by 20 kilograms, which is equal to 5 meters per second squared. Good news is we didn't need to do the y. Of course, if this didn't work out, if I didn't get the answer that I was looking for, ax equals 5 meters per second squared, then I would have just moved on to the y and tried to solve things, and things would have worked out that way. So that's generally what we're going to do. If it doesn't work out, looking at one coordinate, take a look at the other coordinate, and maybe when you put the things together, things will cancel out or work out somehow. That's the hope, and it usually does. Now to C. It says that the block experiences a friction force that causes it to move at a constant velocity. That's good. Constant velocity means the acceleration is 0, right? Draw a free body diagram for the system. Okay, again, identify all the forces acting on the block. I've got mg down, I've got the normal force up, normal. This is the gravitational force. We've got the push, which is equal to 100 newtons, that's the push. And now they tell us that there's a frictional force due to friction. It's moving at a constant velocity, so obviously that's kinetic friction. We know from our theory that the force due to friction is equal to mu sub kinetic then, times the normal force. That's the magnitude of the frictional force. Okay, and of course, if the direction is chosen like this, then that frictional force is obviously pointing to the left, which is negative x, and so that's going to be negative mu k times the normal force. Very good. I think that's everything we need then. That would be the normal force with its direction, frictional force with its direction, the push force with its direction, and the gravitational force with its direction. And we have everything in there for 100% of the points on that question. Now, this is the picture that we have. The question says in D, find the coefficient of friction. So we're trying to find coefficient of kinetic friction between the block and the surface. How can we do that? Well, let's again take what we have. I've got my coordinate system over here. I've got some of my frictional forces and other things. So I'm good to go. I'm going to look at all the forces in the x and then in the y direction. So the sum of the forces in the x direction equals 0. How do I know that? Well, they told us that it's constant velocity. Therefore, the sum of the forces is equal to ma, and remember the definition of acceleration is the change in velocity over the change in time. So if the velocity is not changing, guess what? The acceleration is 0. So you can see that's why we have the sum of the forces equal to 0. It's a Newton's first law situation. Let's go ahead then and sum the forces in the x direction. That is equal to, let's see, the pull or push minus the frictional force. Therefore, Fp minus Fr equals 0. We have the push or pull force is equal to the frictional force. Well, that doesn't help us, does it? We can certainly put in the equation for the frictional force, mu k times the normal force, and then that tells us that the coefficient that we're looking for right now is then equal to this push divided by the normal force. But we don't have these values. We've got the push force, that's 100 newtons, so that's good, but we don't have the normal force, so we're stuck. That's all right. Then just move to the other coordinate. If there were 2 dimensions, then we've got 2 sets of equations. We'll move to that. If there were 3 dimension, for example, if we're moving into the z, we could do that as well. But thankfully, we only have 2 dimensions here. That just makes it a little bit easier. The sum of the forces in the y direction, y we said is up. The sum of the forces in the y direction is equal to, let's look at our picture, normal force, so plus normal force minus mg gravitational force. And the block is just sliding along the surface. It's not jumping off the surface or falling through the surface. Therefore, the sum of the forces in the y direction equals 0. Therefore, the normal force equals mg. And that is equal to, let's see, what was the mass? We wrote it down, 20 kilograms. There we go. So 20 kilograms times 9.8 meters per second squared. Mu sub k is equal to 100 newtons divided by, or 20 times 9.8 newtons, and that works out to be 0.51. So mu kinetic equals 0.51. That is our answer, and we would be getting lots and lots of points for showing our situation over here. Question 3. A person on a weight scale in an elevator moving at a constant speed measures their weight to be 980 newtons. Alright, let me just take a look at that particular picture. If you're moving at a constant speed, that means your net acceleration is equal to 0. So that's a sum of the forces equals 0 situation, Newton's first law. In that situation, they tell us that you measure your weight. That's what the scale tells you its reading is. So in that situation, Fn minus mg, assuming up is positive, equals 0. So the normal force equals mg, and they tell us that the normal force is 980 newtons. Therefore, m, the mass of the person, is 980 newtons divided by 9.8 kilograms, meters per second squared. 9.8 meters per second squared. So the mass of the person is 100 kilograms. Cool. I don't know if I'm going to use that, but just the fact that they told me right at the beginning of the problem we're moving at a constant speed and we measured that, I can work that out. So remember, I told you sometimes I just like to use what they give me, and maybe it'll be helpful later on, but at any rate, it gives me a sense of comfort when starting these difficult questions. Now I can move to the second part of the question. As the elevator comes to a rest, okay, so the elevator comes to a stop, the person experiences an acceleration of 1.2 meters per second squared. And they tell us that it's upward. All right. So the person experiences an acceleration 1.20 meters per second squared upwards. Now, what's the definition of acceleration? Remember, if we're talking about an average acceleration, it's just delta v divided by delta t. And if we were talking about the instantaneous, it would be the derivative of v with respect to t. So delta v, that is, isn't it just the final minus the initial velocity? Yep. Therefore, if a is positive, and it is, it's greater than 0, that means delta v must be greater than 0. Therefore, the final velocity must be bigger than the initial velocity. Which direction was the elevator moving before it stopped? So let's think about the situation. Let's say there's the elevator and it was moving down. So if it's moving down, it's going at a certain constant speed, that's the initial speed, v0, and then it comes to a final stop, right? If our final velocity v is 0, then that means 0 is greater than v0, or it tells you, in other words, that v0 is less than 0. And what does that mean? That means downwards. So we were moving downwards in order to have this upward acceleration as we come to a stop, which makes sense. So the answer is down. Question B. What is the reading on the scale in newtons when the elevator accelerates? What is the reading on the scale in newtons when the elevator accelerates? All right, let's draw our free body diagram. This is the reading on the scale. That's the normal force. That's the force that the scale pushes back on your feet. And you can read that number. And then there's mg. Those are the only two forces that are acting on you. And what's the result of all of that? Well, there's this acceleration upwards, right? Upwards 1.20 meters per second squared. This is our y direction. Upwards is positive. So we can sum all the forces in the y direction. And that is equal to plus the normal force minus the mg, gravitational force, and that's equal to mass times acceleration, that A of 1.2 meters per second squared. So let me go ahead and put everything together. Therefore, the normal force is equal to mg plus ma. If I can pull the m's out, that's m times g plus a, and that's m multiplied by 9.8 plus 1.2 meters per second squared. All right. And in the first part of the problem, I remember we just went and worked out that mass is 100 kilograms. So we can put that in. That's 100 kilograms times 11 meters per second squared. So the force due to the normal, that's the reading on the scale, is equal to 1100 newtons. And here we have then all our points for this. Next, question 4. A 40 kilogram child, write down what we have, mass is 40 kilograms, sitting 1.2 meters from the center of a merry-go-round. Okay, that's a circle. Draw a picture, and there's a radius r. I don't know exactly how big the merry-go-round is. It could be way bigger, but anyway, this is the distance that the child sits from the center. We'll write that down. That's 1.20 meters. Moves with a tangential speed. I'll put that on the picture. There's the speed v of 1.30 meters per second. Obviously, that is changing direction all the time. The speed is staying the same, but the direction is changing. Question. Determine the child's centripetal acceleration. Okay, this is a gimme. The centripetal acceleration is the acceleration due to this rotation. We have that defined in our notes as v squared divided by r. So we can plug that in. That's 1.30 meters per second squared divided by the radius, which is 1.20 meters. And this gives us that AR is equal to 1.41 meters per second squared. And we're done with that question. We'd get a bunch of points for these things, putting all things just as we should, showing the situation. Question B. What is the magnitude and direction of the force on the child? All right. If I drew a free body diagram over here, here's the circle. The child, let's say, is sitting over here. Sum of the forces equals ma. A we've figured out. So we can actually, we don't have to redo the calculation. We can just put the mass of the child in, 40 kilograms times 1.41 meters per second squared, and that gives us the sum of the forces, or centripetal force, is 56 newtons. Now that's not done. That would be about 5 points or 4 points, but it also asks us for the direction of the force on the child. And the answer is, well, it depends, doesn't it? If the child is moving in this direction, when you're over here, the force is going to be pointing in. And when you move on and you're over here now, it's pointing in. But it's always pointing towards the center. And so that's the key. The sum of the forces, that's the magnitude, 56 Newton. The direction is pointing towards the center. And we're good to go. If there is no net force on an object, what's the situation? It is moving in a circle. Well, let me think about that. If an object is moving in a circle, then, well, there is a net force, right? It's changing its velocity all the time, and changing velocity means there's an acceleration. And if there's an acceleration, then of course there's a net force on it, at least one force, as in question 1 in this test. So it's not A. Okay, it is either moving in a straight line at a constant speed, so the V's over here not changing. If V is not changing, then delta V is equal to 0 for this object, right? And we could look at Newton's law. The sum of the forces equals on the right-hand side, what's happening to it? Well, the speed is not changing. So nothing is changing in terms of acceleration at all. So the sum of the forces equals 0. If there is no net force, that is 0 force. It is either moving in a straight line, yes, we check that, at a constant speed, or it's at rest. Well, of course, if it's at rest, the net forces are 0. So that second part is possible. So it could be B. I'll block that because that could be the answer, but there could be another answer, so we'll just check through all the other possibilities. It is accelerating towards the Earth. No, if it's accelerating, there must be something pushing or pulling it, right? That's Newton's second law. So if something's pushing or pulling it, there is a something. There is a net force on it. So it's not C. Weightless, that doesn't make sense. There is no such thing as weightlessness. We can't get the situation. Weight is just the force due to gravity, which is mg. And then it is in free fall. Well, free fall actually means a situation where the only force acting on you is gravity, and that's not the case. So the answer is B. Now let's move on to question 6. An Olympic weightlifter lifts 265 kilograms. Mass is 265 kilograms. From the floor to a height of 2.50 meters. Let's assume up is positive. This weightlifter starts at a distance of 0 in y, then the y is up is positive. So it starts at 0 and it goes up and ends at 2.50 meters. So we could call this y and we can call that y0. So y equals 2.50 meters. It's plus because it's up. y0 equals 0. This is just the way I've set the problem up. Okay, height of 2.5 meters as shown in this figure. Cool. After holding the position for 2 seconds, the weightlifter releases the bar and the bar falls straight down. All right. Question: how much work must the weightlifter do to achieve this feat? So that feat is to get it off the ground and lift it up to a height of 2.5 meters. How much work must the weightlifter do on the bar? Well, if somebody's asking you, remember, work, you're going to have to go ahead and calculate the forces acting on the object. How much work does the weightlifter doing on the bar? The bar is the object. So let me look at the forces acting on the object, on the bar. There's its weight down, mg. And then the weightlifter is pushing on the bar as well. The weightlifter is pushing on the bar as well. And that's going to be the normal force on the weight. If we assume that the weightlifter managed to push this bar up at a constant V, then the normal force minus the gravitational force equals 0, or the normal force is just equal to mg. So the normal force that the weightlifter has to apply to the bar is 265 kilograms times 9.8 meters per second squared, which works to be, let's see, that's about 2,597 newtons. The weightlifter's pushing up with a force of 2,597 newtons, pushing up. And so if the weightlifter exerts that force all the way from the bottom all the way to the top, what's the definition of work? Well, work, W, is equal to the component of the force that is parallel to the displacement. In this particular picture, what is the displacement vector? What does that look like? Well, it's straight up, isn't it? That would be the displacement vector. Displacement in the y direction is y final minus y initial, right? Because displacement is a final position minus an initial position. We're moving purely in the y direction. So displacement is y final minus y initial. And what's the component of the force that's pushing? That's the normal force in the direction of the displacement. It's the whole thing, right? They are parallel to one another. Therefore, the work that is done by the weightlifter in pushing this 2,597 newtons times 2.5 meters, or 6,493 joules or so. Now, when I look at the answers here, that's going to eliminate A. Minus 5,000 joules, it's not that. It's not minus 6,500 joules. It's not 643 joules. It's not 7,000 kilojoules. Could it be that one? So I think it's B is the answer, because this is almost 6,500 joules. We're close. That's within error. But the question says as well, what is the speed of the weights as they hit the ground? What's the speed of the weights as they hit the ground? Well, we're told it's 265 kilograms, and it's 2.5 meters above the ground. And when he holds it there stationary for 2 seconds, it's not moving at all. So it's got a velocity v equals 0. And the question is, what's the speed of the weights? If he just steps out from underneath that, then the weights are just going to come crashing down, because in this case, the free body diagram, he steps out the way. He's no longer pushing up, right? That force goes away. The only force acting on the weights is mg. So this problem actually shows you why it's important to master every single piece of the course as we go along, because here we go. We know if this is our situation, it's going to fall. We can call this our initial speed or velocity right now, 0. And then it's going to fall down, all right? And right before it hits the ground, that's the question. What is the speed of the weights? So we can say, let's take a look at our equations. We've got, if we choose up as positive, then we've got the acceleration down in the y direction is minus 9.8 meters per second squared. We've got our initial velocity is 0. What else do we have? We have our initial position. We'll call this y0. We're starting in this second part of the problem at this point. That's plus 2.5 meters. And where do we end? We're going to end right on the ground at 0 meters. I think that's everything that I have. I don't have anything more. Of course, we could have an x direction, but that's irrelevant to the problem, so we don't want to add extra stuff. No point in doing that. So now we've got to choose an equation. This is like chapter 2 or chapter 3. So I've got v equals v naught, and if we're talking about a y, plus 8yt. I don't know the time. I know v squared equals v naught, y squared plus 2 times ay times the change in y, the displacement. And I have several other equations. So you could go ahead and try to solve for t and then plug it in over here, and we'll get our final velocity in the y direction. But that looks really hard to me. So I'm going to just go to this second equation over here, because actually I have everything there. So vy squared is equal to v naught y, that's 0 squared, plus 2 times the acceleration in the y direction, that's minus 9.8 meters per second squared, times delta y, that's y minus y0, 0 minus 2.5 meters, and that gives me 49 meters squared per second squared. So if we take the square root of that, Vy is plus or minus 7 meters per second. Of course, the plus means up velocity and down means minus velocity, because we defined it that way. Up we chose for our playing field to be positive. So obviously the correct answer would be Vy is minus 7 meters per second, but the maths just gives us the actual mathematical possibilities. There's only one of those, which is actually the physical possibility. Now the question actually asks, what's the speed of the weight? So the speed would be, speed is 7 meters per second, because speed is just the magnitude of the velocity. But if you did say minus 7 meters per second, in other words, you are encapsulating the fact that it's actually downward velocity, I'd give you full points for that. You're totally cool. That's totally fine. And so you'd get all your points for this problem. Now you could have solved this using the work energy theorem, but we only learned about that recently. If you were comfortable doing that, then that's fine. Let me just show you how to do that. If you used the work energy theorem, the net work done by gravity would be exactly opposite to the work done by the weightlifter. So it would be minus, right, 6,493 joules, or minus 6,500 joules. And that, according to the work energy formula, is equal to the change in the kinetic energy. Our initial kinetic energy is 0 when the weightlifter is just holding the pose and the weights are just hanging out there in the air. And the final, so final minus initial, we're going to get, let's see, half times 265 kilograms times V squared equals 6,500 joules. And if you run those numbers, that gives you V squared is 49 meters squared per second squared, which again gives us a speed of 7 meters per second. So that's a lot quicker. The work energy formula is very powerful, very quick. I like it when we can use it. And this is a problem that you could have used, but of course, as I showed you, you should be able to simply use your dynamics equations as well. Question 7. Consider a car rounding a curve on a flat road of radius 50 meters at a constant speed of 15 meters per second. So this car is going around a curve, and we're told that it's moving at a speed of 15 meters per second. The radius is 50 meters. There we go. There's my picture. I'm writing down everything I've got on the picture. Use physics to show whether the car will follow the curve or whether the car will skid. What you're given, the pavement is dry. Okay, that's good. The coefficient of static friction, mu sub s, is 0.60, and we've got free body diagrams looking from the front view and looking from the top view, and our picture then seems fairly clear. All right, so here's our picture on the right hand side, and there's forces that are acting on us. I know that because you keep changing your direction, right? Your velocity is changing its direction, and that means the sum of the forces is not 0. Well, what is the force that's causing you to do that? That's the centripetal force. So the sum of the forces, okay, is equal to MA, and MA is going to be mv squared over r, centripetal force. Well, what's the actual force that's keeping you from skidding, right? So this is centripetal force, mv squared over r. Frictional force is the situation that we're talking about. There it is in our free body diagram. That's what's holding you to the road. And our frictional force is going to be less than or equal to, right, the maximum, that's the static friction, times the normal force. All right. That is to say, that's less than or equal to 0.6 times the normal force when I go ahead and substitute that. So when are we going to skid? I mean, what's the actual physical situation? Well, you're going to skid, aren't you, if this force is bigger than the maximum frictional force, right? If the frictional force is not big enough, you're just going to skid out. So as you start going faster and faster and faster around this circle, the frictional force is going to get bigger and bigger and bigger until you're going to get a maximum frictional force of 0.6 times the normal force. So if we could figure this out, we could compare these two forces over here, and if the centripetal force is bigger than the frictional force, then we're going to skid. And if it's smaller than or equal to the frictional force, we won't skid. Okay, we're stuck though, because how do we compare these two things? What do you think? Well, I can go ahead, and we've just looked at the sum of the forces in this radial direction. There's another direction, isn't there? The up and down direction as well. So let's sum the forces in the up and down direction. And if I choose up as positive, then we have in the free body diagram, the sum of the forces is the normal force minus mg. And what's happening in the up and down direction? Is the car jumping off the road or falling through the road? No, it's doing neither. So it's not actually changing its motion in the up and down direction. That means it's a Newton 1 situation, Newton's first law, the sum of the forces equals 0. That tells me that the normal force equals mg. Okay, that's cool. So I can go and take that and plug it in over there. So the force due to friction is equal to 0.6 mg. Oh, that still doesn't help me, does it? It still doesn't help me because I don't know what the mass is. What's the mass? Well, actually, to solve the problem, I don't need to know what the mass is, remember? I just need to show that the frictional force is bigger than the force due to our centripetal motion. How can I do that? Well, I need to show that mv squared over r is less than force of friction, right? If this is true, then we're not going to skid. Well, if I put this in, then I've got mv squared over r must be less than 0.6 mg. That's good. I can cancel the masses out. So if I can show that v squared over r is less than 0.6 g, then we're not skidding. We're good. So let's run the numbers. What is v squared over r? Let's see, that's 15 meters per second squared divided by 50 meters. And that works out to be 4.5. And then, so this number over here is 4.5. The right-hand side is 0.6 times g. 0.6 times g, you multiply that, 0.6 times 9.8. That's 5.88. Okay, so is 4.5 less than 5.88? Yes, it is. Answer, it will not skid. The final question. Every few hundred years, most of the planets line up on the same side of the sun. So we've got the sun over here, we've got planets doing their thing. Calculate the total force on the Earth due to Venus, Jupiter, and Saturn, assuming all 4 planets are in a line. The masses are, the mass of Venus is 0.815, mass of the Earth, mass of Jupiter is 318 times the mass of the Earth, mass of Saturn is 95.1 the mass of the Earth, and the mean distances of the 4 planets from the sun, okay, Venus, okay, so Venus is a certain distance, it says 108 million kilometers, million kilometers, that's gigameters, 108 gigameters, there's Venus, okay, alright, Venus is over there from the sun, and then the Earth is 150 million kilometers. I'm just drawing my picture, so that distance now is 150 million kilometers, that's gigameters, because a million times 1,000 is a billion, giga, and that's the Earth. And then we've got Mercury, Venus, let's see, 778, that's Jupiter, that's the next one in the order of the planets that was listed, 778, so here we go, 778 gigameters, that's Jupiter. And then finally we have Saturn, and we're told that that's 1,430 gigameters, Saturn. The question is, assuming all 4 planets are in a line like this, they're 1, 2, 3, 4, calculate the total force on the Earth due to Venus, Jupiter, and Saturn. So we better draw a free body diagram. So let me do that. Here's my planet Earth. I'll just go put it over here. Venus is going to pull it which direction? To the left, right? This is going to be the force on Earth due to Venus, to the left. Jupiter is going to pull it to the right. So this is the force on the Earth due to Jupiter. Saturn is also going to pull it to the right, the force on the Earth due to Saturn, and those are all the forces. So the net force on the Earth is going to be the sum of all of those. So I've got to choose a coordinate system. It's a one-dimensional problem. I'll just choose positive to the right. Therefore, the sum of all the forces on the Earth is equal to, let's see, positive force due to Saturn plus the force due to Jupiter minus the force due to Venus. Okay, so those are all the forces, and we could go ahead and work this out. We're going to have to work out the radiuses, because actually we're talking about gravitational force, and our equation of Newton's gravitational law is G times m1 times m2 over r squared, and of course this is G, which is 6.67 times 10 to the minus 11 Newton meters squared per kilogram. What a horrible unit that we have over here for the gravitational constant. Okay, so we have to calculate the radius. That's the distance from the center of Earth to the center of these other planets. So let's work that out. The distance from the Earth to Venus. Let's see, that's going to be, if I look at my picture over here, 150 minus 108. You can see how drawing a picture makes it easy to figure these things out. 150 minus 108 gigameters, which is 4.2 times 10 to the power of 10 meters. All right, now we can go ahead and plug all those numbers in. So the force on the Earth due to all the planets is, let's do Saturn first. That's equal to big G, mass of the Earth, times mass of Saturn, divided by the distance between the Earth and Saturn squared, plus big G, mass of the Earth, okay, now it's Jupiter, mass of Jupiter, divided by the distance between the Earth and Jupiter squared, and then minus big G, mass of the Earth, times mass of Venus, divided by the distance between the Earth and Venus squared, and we're good to go. I'm going to pull out the thing that's common. That is G times the mass of the Earth squared. And so we can go ahead and put all the numbers in. That's 95.1 divided by 1.28 times 10 to the 12 meters squared, plus 318 divided by 6.28 times 10 to the 11 meters squared, minus 0.815 divided by 4.2 times 10 to the 10 meters squared. And now it's an algebra problem. That gives us, let's put all the numbers in explicitly, 6.67 times 10 to the minus 11 newtons meters squared per kilogram squared. That's big G. Mass of the Earth squared is 5.97 times 10 to the 24 kilograms. Okay, squared. And finally, all of these numbers work out to be 4.02 times an incredibly small 10 to the minus 22 meters to the power of minus 2. Or we've got the whole thing then, if we've done our calculation correctly, is 9.56 times 10 to the power of 17 newtons, or to the correct number of significant digits, that's 10 to the 17 newtons. That is the answer. And if we wanted to, we could figure out now what would be the acceleration of the Earth due to all of this, because the sum of the forces equals ma. And you'd see that the Earth is hardly moving at all because of these big planets. And if the Earth is moving, then what could possibly be doing that? And the answer would be the Sun. The Sun is far more massive, and you can do that calculation if you know the mass of the Sun. Or if you look at the motion of the Earth, you can conversely find the mass of the Sun. But I didn't ask that in the question, so we don't need to worry about that. Here's the answer, and we're done. Congratulations.